Now let's talk about the equations of planes. So you need 3 non-collinear points to define a plane, whereas you only need 2 to define a line. And because of that, you might think that you need more information than you need. You may need more information to define a plane than you do a line. Remember, with a line, we need a point and a vector. It turns out that we can also specify a plane by a point and a vector. We can specify it by a point that's on the plane, and then a vector that is perpendicular to the plane. And that uniquely specifies the plane. Here's our picture right here. So to get, we call this vector n here that's perpendicular to the plane a normal vector. Now for any other point P on the plane, we're going to use the same convention here. R is a position vector for P. R0 is the position vector for P0. So the vector between P0 and P0 can be written as R minus R0. And this is lying in the plane, so it's got to be perpendicular to n. So therefore, n dot r minus r0 is equal to 0, which gives us n dot r is equal to n dot r0. This is a vector equation for the plane. We just need the same amount of information as we do for a line in order to get an equation for the plane. We can write this vector equation a lot more explicitly as a scalar equation. So let's say a plane contains the point P0, x0, y0, z0, and it's orthogonal to the normal vector with components a, b, c. We get a scalar equation by writing this out explicitly for all the points P, x, y, z on the plane. The dot product of n against r minus r0 is equal to a times the difference of these coordinates plus b times the difference of these coordinates plus c times the difference of these coordinates. Great. This is pretty clearly just a dot product of this vector and the displacement vector from P0 to P. Great. So let's find an equation of the plane through 4, negative 1, 0, perpendicular to 1, negative 2, 3. Well, a is 1, x0 is 4, so we get that. B is negative 2, so minus 2 times y minus negative 1, so y plus 1, plus 3, c is 3, times z minus 0, and that's equal to 0. And simplifying, we have x minus 4 minus 2, y plus 1, plus 3z is equal to 0. Great. So the last form, the scalar equation, quote unquote, is very similar to point-slope form. Point-slope form is something where you can read off the slope and the point that a line goes through very easily. And the last form, it's very easy to pick out the point that we were looking at. It's very easy to pick out the normal vector to the plane. Well, here we can also rewrite things that are a little bit closer to slope-intercept form, where we don't have something times the quantity x minus something, something times the quantity y minus something, whatever. So if we really just multiply out, we can get ax plus by plus cz plus d equal to 0, where d is given by this formula. You don't need to memorize this. All you have to do is multiply a through x minus x0, b through y minus y0, c through z minus z0, and you get this. Great. And this we might call a general linear equation, sort of the general form of a linear equation. This is often an easy form to graph from because it's very easy for us to find the intercepts. And really, to plot a plane, a perfectly valid way of plotting a plane is to plot any 3 non-collinear points. And generally, a plane will hit each axis exactly once, and that will give us 3 non-collinear points, the intercepts. That's not always going to work, but in this case it does work. So in most cases it does. So let's check this out. So we want to find the x, y, and z intercepts. So the x-intercept occurs when y and z are both equal to 0, which gives us 6x is equal to 24, which gives us x is equal to 4. Note that here I really have the 24 on the right hand side. It doesn't really matter whether you have d on the left hand side or minus d on the right hand side, whatever. so long as you have something times x plus something times y plus something times z, maybe plus a constant is 0, or maybe that's equal to something, whatever. These are both valid. I just had it this way because it made the algebra a little easier. So my y-intercept is when x is equal to z is equal to 0. So I got 8y is equal to 24, or y is equal to 3. And finally my z-intercept is where x is equal to y is equal to 0, which gives me 12, z is equal to 24, or z is equal to 2. So let me draw my coordinate axes here. Here's the origin. The x-intercept is 4. So along the x-axis, I'll go 1, 2, 3, 4. There is my point 4, 0, 0. Y-axis, I'll go at 3, 1, 2, 3. There's my point 0, 3, 0. Finally, z-axis 1, 2. There's my point 0, 0, 2. And just to illustrate that I'm looking at the plane here, I'm going to draw lines connecting these guys. And that will sort of suggest that, okay, this triangle and really everything inside of it lies on the plane that we are looking at. If you want to, shade it in a little bit, like that or something like that, okay, there's the plane we're looking at, great. We're just imagining that it extends beyond this, but we understand that if we have a piece of a plane, a substantial piece of a plane that actually has some area, then it's understood that we really mean the rest of the plane too by extending it. And it's enough information with these 3 points here to get back the plane that we're looking at too. So this is an important question. Given 3 points, can we find an equation for the plane through those 3 points? And the answer is, well, yes. And this is very similar to what we do when we would like to find the equation of a line through 2 points. Remember, if we're looking for the equation of a line through 2 points, we use those 2 points to construct the slope. Then we use the point-slope form, say, to get the equation, using one of the points to get the equation of the line through those 2 points. Here, the analog of the slope, really the thing that tells us the direction of the plane, is our normal vector, which really tells us what direction is perpendicular to the plane and therefore specifies what directions are parallel to the plane. So, the first thing we're going to do is figure out what the normal vector is, or a normal vector is. So what we'll do is, here we've got 3 points, 1, negative 2, 3, 4, 2, 1, and negative 2, 3, 5. And to figure out the normal vector, we're going to realize that if I take any displacement vector between any 2 points here lies in the plane. So if I take 2 displacement vectors and they happen not to be parallel, then their cross product will be something that is parallel to the plane. So sort of the picture here is this. I've got P, Q, and R, and assuming that P and the vector from P to R and from P to Q are not parallel, then PQ cross PR is going to be perpendicular. And following the right-hand rule, this is actually going to be a vector pointing down, PQ cross PR, and that'll be perpendicular to both of these guys. Great. So, PQ, I subtract the coordinates of P from Q. 4 minus 1 is 3, 2 minus negative 2 is 4, 1 minus 3 is negative 2. Similarly, PR, the vector, is negative 2 minus 1 is 3, 3 minus negative 2 is 5, 5 minus 3 is 2. Then I take their cross product to find the normal vector n. PQ cross PR, that's ij, the determinant ijk. The first row, second row is 3, 4, negative 2 from PQ. The third row is negative 3, 5, 2 from PR. And I leave this to you to evaluate that the cross product does equal 18i plus 27k. And so we can take an equation to be, the scalar form would be 18 times x minus, let's use p, x minus 1, plus 0 times, because there is an implicit plus 0j here, so the y component of the normal vector is 0. So 0 minus negative 2, 0 there, plus 27, which is our c, times z minus the z coordinate, which is 3. That's equal to 0. This goes away, and we're just left with 18 times x minus 1 plus 27 times z minus 3 is equal to 0. If you'd really like to, you can go ahead and figure out a linear equation for this guy too, but this is really good enough.